everyone. So today we are going to discuss about relativistic momentum. Okay, recall that in Newtonian mechanics, we can say that momentum is conserved. The total momentum of a system is conserved after collision. So the total momentum before and after collision, they are equal. So what do you think will happen if this time an object is moving at the speed of light? What will happen to their momentum? Is momentum still conserved? Okay, we are going to find out. Take note that according to the special relativity postulates, number 1, that the laws of motion are the same in inertial frames of reference. So let's take a look at this if really momentum is still conserved.
Okay, so let's take a look at this illustration. Okay, wherein we have here the
Okay,
distance.
take note that you have learned in mechanics that when bodies
between the two
interact,
balls would
the
be
total
y.
momentum is constant, provided that the net external force acting on the bodies in an inertial frame of reference is equal to 0.
We have ball
So
A
there's
here.
no net force acting on the system. Okay, so I want you to look at the illustration at the left.
It has an
You can
upward
see
velocity.
here two balls. One is ball A at a frame of reference S
and then you
frame.
have ball B.
So that S frame is at rest, so it's not moving. And then the other one, B,
with a downward
so you can see
velocity
here
VE.
above. This one
Now,
is ball
they will
P
collide,
at S prime
but afterwards
reference.
they will bounce
So
back.
S prime is
We are going
moving
to
at a
consider
constant
two frames
velocity.
wherein we have here an
So we will
observation
check what
from
will
S
happen to their
frame,
momentum if
and
A
then
and
an
B will
observation
collide.
from S prime
Looking at the
frame,
illustration again,
wherein
so you
S
have
prime
here
frame,
S frame and
is
then S
our
prime
reference
frame.
point,
As I have
which is
mentioned, they are
moving.
in relative motion.
So how
Let
are
us
we
just
going to
consider S
express
prime to be
their
moving to your
velocities
right.
and their momentum?
Take note of the velocities.
So
Velocity
take note
of
here
A
that velocity
at
A
S frame of reference
is
is
equal
equivalent to the velocity
velocity
of B at S
prime.
prime frame of reference. So take note of that.
Then
That's
let's
why
take a
we
look
have
at
there
the distance
prime, because it's
each will
considered that
cover.
it's located
Take
at
note we
S
have here
prime.
velocity
So
equals
what?
distance
How
over
do we
time.
describe their momentum? Okay, so now I want you to pay
Now,
attention
if
on
we
the
are going to
derivation
consider
of
the
the
round trip
relativistic
travel of
momentum. Okay.
ball A,
So let's get
so it will
started
travel
deriving
upward and then
relativistic
downward.
momentum.
So the round trip will be 1/2 y times 2. So let's take a look at the velocity of A. The distance it will cover will be half of y. However, since it will bounce back, that will be twice. Okay, divided by, if we are going to consider at S frame, so that will be the proper time T naught. Take note, this is according to S frame. So we have here the velocity of A is equivalent to 2 y over 2 divided by T naught. So we can now cancel out 2. So we now have here VA is equivalent to y over proper time T naught. So that's our velocity for A. then you can also express the proper time in terms of VA. So proper time now is just equivalent to Y divided by VA. So that is our equation based on S frame. Then now let's solve for the equation for VB or for ball B. Okay, now let's take a look at the motion of ball B in terms of S prime frame, or this one, it's the moving frame of reference. So let's have, again, velocity equals distance over time. But for this time, we are looking for the velocity of ball B, so VB prime, equals the distance it has traveled, so it's the same. For a round trip, it will travel 1/2 y, and then it will bounce back 1/2 y again. So that will be 2 1/2 y. According to S prime frame, so this is according to S prime frame. In the previous example, that is according to S frame. So here, according to S prime frame, the time is also the proper time T naught. So we have VB prime is equal to Y over T naught according to S prime frame. So it's important to note that this is according to S prime. So if we are going to express proper time, we also have an equation wherein T naught, proper time, so in S prime frame, we have T naught equals Y divided by V B prime. So that is our expression of proper time in S prime frame. Okay? So let's continue. So let's take a look at this equation. Again, the velocity, or again, ball B is at S prime frame. So we were able to express its velocity in the earlier slide. And now, we are going to check it according to S frame. So S frame, take note also that S frame is at rest. And then we have S prime frame, okay, moving at a velocity V. Prime, where ball B is found in the S prime frame, and then ball A is found in the S prime. Then they were released and then they collided. Then let's take a look at how we can express now the velocity of B or ball B according to S, or according to S frame. Okay, for S frame, we have velocity B equals the distance. As I have mentioned, it will travel twice 1/2 y. But this time, the time is no longer proper time because the S prime frame is moving relative to S. Our observer is at S time t instead of proper time. So tandaan nyo, pag sinabi nating proper time, that means that the object is at rest relative to the observer. That's why we have ball A at S frame, we consider proper time t naught. Then we consider also a ball B at S prime frame, the proper time is also t naught. But this time, we are looking at the velocity of B, or ball B, found in the S prime frame, but according to the observer in the S frame, which is at rest. Kaya, we will consider time t. Hindi siya t naught. Not at the proper time. Okay? So, solving this one further, we now have, from time dilation, take note that we have t equals t naught divided by square root of 1 minus v squared over c squared. So we can use this relationship wherein we have now the velocity b. Okay, we can now express velocity b. This is according to S frame. Our velocity b is y divided by t naught over square root of 1 minus v squared over c squared. There. So solving this one further, we will have a velocity b. Okay, I will use this one. Velocity b equals 2 1/2 y, so that will just be y, divided by t naught, then multiplied by square root of 1 minus v squared over c squared. Kasi that will be y divided by t naught divided by 1 minus v squared over c squared. So we just get the reciprocal. So we now have here the velocity of ball B is equivalent to y times square root of 1 minus v squared over c squared equals t naught, or our velocity B now, according to S frame, equals y square root of 1 minus v squared over c squared divided by t naught, or the proper time. So solving this one further, we can now look into the momentum. So let's take a look at the momentum. Looking at the momentum for A, we have P, A equals MAVA. Wherein we have solved earlier that we have now MA, our VA is expressed as y divided by t naught. Okay, this is again according to S frame. So that will be our momentum for object A. But for object B, our momentum is PB is equivalent to MB VB. So that will become MB, and then we use this expression. So we have y square root of 1 minus v squared over c squared divided by t naught. So again, this is our momentum for object A. According to S frame, MA equals PA equals MA over T naught. And then also, same frame, according to S frame, we have here momentum of B equals MBVB. And then let's substitute that velocity. We have Y square root of 1 minus V squared over C squared over T naught. Okay, so now let's analyze this one. Okay, do you think momentum A is equal to momentum B? Since they have the same velocities. Okay, so if you're going to take a look at this, we have MA y over T naught, and then we have here MB y over T naught square root of 1 minus V squared over. Okay, looking at this one, we have momentum A equals momentum B. Let's take a look at this. Do they have the same momentum? Since they have the same velocities? If you are going to check this one, they will have the same momentum if there will be a relationship wherein the mass of A is not equal to mass of B. Because if we say that mass of A is equal to mass of B, obviously, momentum is not conserved. Because you can see here, there's a factor square root of 1 minus V squared over C squared, which is always a factor less than 1. But if we can analyze now that they will be the same, or their momentum will be the same if and only if mass A is equal to square root of 1 minus V squared over C squared of mass B. Then we can say that momentum is conserved. Okay, based on our calculation earlier, we can also express mass of B. So you have mass B is also equivalent to mass of A divided by square root of 1 minus V squared over C squared. Okay, this factor will make momentum conserved if MB is equal to MA divided by square root of 1 minus V squared over C squared. Therefore, we can say that in relativity, velocity affects the mass of the system. So mass as a function, therefore here, mass as a function of velocity is equivalent to mass divided by square root of 1 minus V squared over C squared. So that will be our equation, where in momentum again, it's still mv our relativistic momentum will be equivalent to mass, which is mass divided by square root of 1 minus v squared over c squared times the velocity. Okay, so we can actually express this one, the 1 over square root of 1 minus v squared over c squared, then mv, we can express this into gamma mv. Okay, so we now have gamma equals square root of 1 over square root of 1 minus v squared over c squared. So that is our relativistic momentum. Okay, so again, take notes. This one is the gamma.
But in relativistic momentum, mass is a function of velocity. Okay, the next thing that we are going to review is Newton's second law of motion. Recall that in Newton's second law, we have here force is equivalent to the mass times the acceleration, or we can also say that acceleration is directly proportional to the force, then inversely proportional to the mass. If we are going to express our derivation, we now have we also have an expression wherein object is equivalent to the change in the momentum over change in time and the mc squared. So let's check where did that equation come from. Okay, let us recall that we have here in mechanics, impulse is equivalent to the change in momentum. So you can see there, F delta T equals M delta V. And then deriving it further, let's divide the whole equation by delta T, and then you now have F equals M delta V over delta T, wherein recall that mv is equivalent to momentum, mass times velocity. Since we have there m times the change in velocity, then we can consider that the numerator is a change in momentum. So you now have force is the derivative of momentum with respect to time. Recall that in the derivation that we have relativistic momentum is equivalent to gamma mv, wherein gamma is the 1 over square root of 1 minus v squared over c squared. Then you multiplied it by mass times velocity. Therefore, another expression for force is that the change or the derivative of the gamma mv with respect to time. Okay? When we say derivative, it's actually the change or the delta. So we have the delta gamma mv over the delta t. Okay, let's continue. Okay, so now we are going to derive relativistic kinetic energy. Okay, so let's derive work, or the total work done. Recall in your mechanics that it's equivalent to delta Ke, or a change in kinetic energy. And also work is equal to force times the displacement. Now we are going to relate kinetic energy and work done. So we have kinetic energy is equivalent to the integral of F ds, where F is the force and then ds is the displacement. Okay, we set the limit from 0 to s. So based on the derivation that we had, we also have force is equivalent to the delta P over delta T, or the derivative of momentum with respect to time. So let's substitute that expression to force. We will now have kinetic energy equals the integral of derivative of momentum with respect to time, and then ds. So let's derive it further. We now have the integral from 0 to s. We have the expression for momentum gamma mv based on our derivation earlier. And then we have here dt and then ds. Okay, equals. So we can now have ds over dt as the velocity. And then we have the delta gamma mv, or we have the derivative of gamma mv. Okay, so let's continue with our derivation. We now have kinetic energy equals the integral of v, then derivative of gamma mv. Okay, our limit is from 0 to s. Okay, let us recall also that gamma is equivalent to 1 square root of 1 minus v squared over c squared. So gamma is not a constant. Kinetic energy now is an integral of v, then the derivative of mv, square root of 1 minus v squared over c squared. So we cannot just simply factor out gamma because it's also a factor of velocity. Okay, let us recall in calculus the integration by parts, wherein we have the integral of x dy is equivalent to xy minus the integral of y dx. Okay, we will use this integration by parts, okay, so that we can derive an equation for kinetic energy. Wherein that is, we have to identify x and y. So we now have kinetic energy Okay, ang dx natin, or ang x natin is v, and then the dy would be the mv square root of 1 minus v squared over c squared. So that will be our expression for xy minus the integral of y dx. So our y is mv divided by square root of 1 minus v squared over c squared. Okay, dv. Because that will be our dx. So that's an integral. Okay, so that will be the expression for integral of y dx. So let's continue. We now have integral of mv dv square root of 1 minus v squared over c squared. So we will solve this expression. So how can we solve for that? We can factor out m being constant. We have v dv square root of 1 minus v squared over c squared. So how do we solve for this integral? Okay, take note that we have a strategy in calculus. Let u be equal to 1 minus v squared over c squared for this expression. Then our du, or the derivative of 1 minus v squared over c squared, since 1 is constant, so it has no derivative. But we have the derivative for the second expression. We have one over c squared, okay, 2v dv. So that will be negative. Okay, so let's solve it. Let u equals 1 minus v squared over c squared. Okay, and du should be negative 1 over c squared 2v dv. Okay, we now have mass integral of v dv over square root of 1 minus v squared over c squared. So we can now express v dv into du based on that equation. Okay, we have here v dv is equivalent to negative c squared over 2 du. So we will use this expression. So let's substitute this expression for v dv. We have mass integral of negative c squared over 2 du over, that will be our u, but raised to 1/2. So that is u raised to 1/2, or that's square root of u. Okay, so we now have negative mass c squared over 2 integral of, so we can place it on top, or on the numerator we now have u negative 1/2 du. So we can now get that integral. So that is negative mc squared over 2, okay, plus 1. Whatever is the answer there, that will be our denominator. So that is u Negative 1/2 plus 1 will be positive 1/2 divided by 1/2 from 0 to V. So we can now cancel 2. We now have an expression of negative mc squared square root of 1 minus v squared over c squared. Limit is set from 0 to v. Okay, let's combine everything. We now have kinetic energy equals mv squared divided by square root of 1 minus v squared over c squared. So originally it was minus, but we have negative, so minus negative, it will become positive. Mc squared square root of 1 minus v squared over c squared. Limit from 0 to v. So let's continue. We now have mv squared divided by square root of 1 minus v squared over c squared plus, okay, we substitute now v and 0, so we have mc squared square root of 1 minus v squared over c squared minus, so that is the final, yung v. Then we have the initial is 0. mc squared square root of 1 minus 0, let's substitute 0 there, over c. So that will become 0. So let's continue. We have mv squared plus mc squared square root of 1 minus v squared over c squared all over square root of 1 minus v squared over c squared. Then we have minus mc squared. So let's get the LCD, or the least common denominator. For this, we have all over 1 minus, or square root of 1 minus v squared over c squared divided by this equals 1 times the numerator mv squared. So this expression divided by 1 times that, you will now have mc squared 1 minus v squared over c squared. Since nag-multiply na tayo ng dalawang square root, so that will be squared. There, minus mc squared. Okay, so we have here mv squared divided by square root of 1 minus v squared over c squared plus mc squared square root of 1 minus v squared over c squared, then you square that, minus mc squared. Next is mv squared, so that will be equal to mv squared square root of 1 minus v squared over c squared plus mc squared 1 minus v squared over c squared. Okay, just put the equal sign at the left, over square root of 1 minus v squared over c squared minus mc squared. Okay, so that's a long derivation for kinetic energy. We have mv squared over square root of 1 minus v squared over c squared plus, okay, we can distribute mc squared over square root of 1 minus v squared over c squared minus for relativistic momentum and relativistic kinetic energy. Squared. If you have questions, okay, just write down in the comment down below or in the comment in the comment box in our group. Over c squared. So next meeting, we will also derive a relationship between energy and momentum. So you can now see an expression which we can cancel out. So cancel this one before we proceed to the next. Squared over square root of 1 minus v squared over c squared. So please try to understand each part and same quantity. So let's cancel it out. Happy learning, everyone! Bye! So that we can now have the final expression for kinetic energy. So just put equal sign, that will be equals mc squared